Here we're going to look at waveform parameters now in more detail, and specifically for rectangular waves in this video, and then we'll do another video that kind of zooms in on sine waves and some of the specifics there. So if you remember, since we're in the AC course, voltage is changing in time. It makes things more complicated. There's more to address. So that brings us to all kinds of parameters that we deal with. So if you remember, we've got the things like pulse width, space width, peak voltages. Here we have two, they're not the same, so we would probably call this the positive peak voltage, and here we have a negative peak voltage, and they're different. I forgot to make that one negative. Let me put that in there. It wouldn't have to be negative. You could have offset. That's the center of the waveform, remember. You could have offset that pushes the whole waveform up into the positive ranges of voltage. But so yeah, so we have our positive peak, that would be this, sitting right here. We have our negative peak sitting here. Not that it has to be a negative peak, like I said. Where is my offset? V offset, do you remember? That's always center of the waveform. So, and this is, I guess, the three main parameters I want to zoom in on are those, let's see, V offset, let's write them down here. V offset, V average, and VRMS. That's what we want to really look at. But the offset is the center of the waveform. And so let's identify that. If one peaks at 4 volts, the other peaks at -2, the center of this waveform, what do you think? Equidistance from either peak. Looks like 1 volt, right? 1 volt would be right down the middle. Yeah. So we would say that we have 1 volt of offset in this waveform. And you can always double check it, of course. I always look and say, I got my 1 volt calculated, and is it 3? It's 3 volts away from 4. It's 3 volts away from -2. Of course, mathematically, you would just maybe add those, right? 4 plus -2, and then divide by 2 to find the center. Yeah. So. Okay, what other parameters? Well, if we have pulse width and space width, of course, all together, we know that's period, right? So we've got T, and that's just the whole thing, the whole time of the waveform, right? All the way across there is T. Pulse width plus space width, right? We've got frequency, that's just the inverse of T. Let's see, are we missing anything? Peak. You could say peak to peak. We do have, it's true, we have a 6 volt peak to peak, just sort of getting them all out there. This is what we deal with waveforms. Might have them all there. Okay. So let's tackle average. There's a universal formula for rectangular waves that's important to know. And it just is a way to calculate what the average voltage is over the entire waveform. These are periodic waveforms, so it would be the average, the full cycle average. And the average, of course, like we said, it's just if you take all the voltages over time and then see on average what the voltage is. So the formula is pretty simple. It simply takes into account how much time you're at this voltage and how much time you're at this voltage. So it's going to be, to get the overall average of any rectangular wave, square waves included, offsets included, no matter what you're dealing with, this formula works for everything. And then there's variations of this formula because things simplify or drop out of the equation, depending on things like if you have one of your peaks is at 0 volts, for example, like in the 5x5 circuit, you'll see how some terms drop out quickly then. But let me give you this universal one, and all it is taking into account how much time, right, pulse width you are out of the period, the total time, how much of that time are you at positive peak? And how much time out of the total time period are you at this voltage, whatever that voltage is. And again, I mention it again, I'm identifying the two peaks as the more positive peak and the more negative peak. It doesn't mean that this has to be negative voltage. It doesn't mean that this has to be positive voltage. Off to the side here, we can scribble a little something. For example, I can have a rectangular waveform that's offset by quite a bit. And so the whole waveform would be just up here. See, it never does go negative, does it? In fact, it has a little bit of a whole lot of offset and never even touches zero the way I drew it. So, but this is still the more positive peak, right? And this is still the more negative peak. Yeah. So just let you know, you can push these waveforms anywhere you want with offset. You can push them up, push them down. They can be completely negative, completely positive. It does change, of course. We described in another video, it wouldn't be AC now, would it? It would just be pulse DC at this point because the current's not reversing direction. So here you have the universal the universal formula to get the average of any rectangular wave. I think you can see things drop out, like if this peak is at 0 volts, like in the 555 circuit, then this whole part of the formula goes to 0, right? If this is 0, all this is 0. Yeah. And your average voltage then is just this. Does that look familiar? Duty cycle, right? Duty cycle times the peak. So we did use that in some of the little exercises we did previously to this. So you can see how the universal formula here, it has some variations depending on the specifics of your waveform. But keep this one in mind. This one is always what you can start with. You can simplify the formula as, you know, as it pertains to different waveforms. But this is what I like to call the universal formula. And again, maybe if you caught it, but you know, how much time out of the period or the total time are you here? Are you at this voltage? And how much time out of the period are you at this voltage? And you put that together, you've got the overall average. Yeah. Well, we can do a universal formula for RMS also. It's pretty easy because if we remember what RMS is, it's the square root, the root of the mean of the squared values. So root mean square, so you square everything, all the values in your waveform, then you average those squared values, and then you square root that. That's how you go. We can do that with this formula. Well, let's get the original formula for average here. So pulse width, period. Okay, let's get it down here. Positive peak. You're just putting those together, and how much time out of the total time are you sitting at this voltage? Okay. So to get to the RMS, you have to square everything, square all the values. So I'm at this peak, whatever the peak voltage is, I'm going to square it. Whatever my negative voltage, I'm going to square it. It's pretty easy for rectangular waves because you are only dealing with 2 voltage levels. You know, some of the time you're here and some of the time you're here. So we square those, and then this original formula does do the averaging of these squared values. See, they're squared now. This averaging is still in place. That doesn't change. So I've gotten pretty far here. I've gotten the average or the mean of the squared values of my rectangular wave. Only thing left to do is square root it. There you go. So that's the universal formula for RMS. And one of the biggest things I want to get across to you in this video is how different average voltage and RMS voltage are. So remember, RMS, this is the one, RMS is the one that tells you what the load is going to look like, how it's going to look compared to if you were to run it on that same value of voltage that as DC. So like if I have, you know, a 10-volt lamp, let's say, and I hook it to 10 volts DC, and then I want to know what it'll look like with a rectangular wave applied, it would have to be 10 volts RMS, not average. That gives me the same look. Okay. And let's do some examples. I think now we can move over. I have some on the left side here that are already drawn. We can just go through those. We could even look at this one before we head over there. I just put one up here just randomly. Let's see what we have here. You know, it's at 4 volts for 1 millisecond. It's at -2 for 2 milliseconds. It's spending twice as much time down here and half as much time up here. Can you see just from that statement, the average voltage, it looks like it's going to be 0 volts. Yeah, I think so. And then, but we could of course plug it into the formula here. And the other thing to notice though is, with that said that the average voltage is 0, if I connected this to a lamp or any resistive load, it's not going to behave like 0 volts is applied. It's going to be hit with this voltage, and then it's going to be hit with this voltage. That is no way going to look like applying 0 volts DC to it. So you can see right away, I think, that the average voltage isn't really the voltage that we're interested in. Electrically, we want to know the RMS voltage. And if we do the RMS, we get a whole nother answer. It's certainly not 0. You know, we would square this and square this. Notice how the squaring that you do in the RMS takes away the negative of the negative voltage. And that's important to understand. I mean, electrically, the lamp doesn't care which direction the current's going through it. So it's going to get 4 volts of pressure in one direction and then 2 volts of pressure in the other direction. But in either case, it's getting current being pushed through it here and here. So that's another reason why RMS is the calculation of interest that we use for electricity. Average doesn't really give us an idea of what's going to be happening, but RMS does. So we can head over here and look at some more examples. So here's a very simple example, right? And I just put numbers in. This could be milliseconds. You know, if you want 4 milliseconds and 4 milliseconds, I just the little squares from the graph paper are a little faded here, so I thought I'd better write in sort of the ratios of pulse width to space width. It's spending an equal amount of time at 10 volts, and then it's another equal amount of time at -10 volts. It's centered on 0 volts, isn't it? So the offset is 0, the center of the waveform 0. The average voltage again is 0 volts here because overall, you know, if you're at 10 volts and then at -10 overall, it's a 0 volt average. But again, we can make that point. You connect a lamp to this and think about what you might see as and we just use a lamp because that's easy to get a visual on, but I mean, it could be a heater, it could be any resistive load. Can you get a sense of what it would look like? I mean, it's going to see 10 volts for sure for 4 milliseconds if we want to use milliseconds. And then what? It's going to see 10 volts for 4 milliseconds again. And so what if it's going the other direction, the current? I'm not going to see that. I don't care about that. The lamp certainly doesn't care which way the current's going. It's not, doesn't have polarity, neither does a heater. So for resistive loads, for all practical purposes, that's the same. It's got 10 volts of pressure and it'll have the resulting current. It'll have 10 volts of pressure, yes, the other direction. So current will go the other direction, but it doesn't change the fact that you'll have the same voltage, pressure, and the same current. So you'll have the same power, you'll have the same brightness. Do you see that that lamp is going to just see 10 volts all day long? 10 volts, 10 volts, 10 volts. And when you do the RMS calculation with the universal formula here, you will come up with that truth, that the RMS voltage for this waveform is 10 volts. And the lamp will look like 10 volts is applied. So if you apply this or 10 volts DC, it'll look the same. And again, we can emphasize that the average calculation, we don't really care about that so much. It's not really telling us or instructing us on what it's going to be happening electrically. So, an average voltage of 0 volts could be misleading, right? If you just left it at that in your mind. RMS is more enlightening. 10 volts. So, okay, so I kind of beat that to death, but I hope you can see it, and I hope you can see it easily. One of the big differences, it's a great simple illustration of the difference between average and RMS. Let's look at the next one. We've got maybe equal time again spent at each peak, 4 milliseconds if you like. But now I'm at 15 volts for 4 milliseconds, and then I'm at negative 5 volts. I can see I have offset, of course. And what is the offset? Well, 15 plus negative 5 divided by 2 puts me at 5, and then you can double check it. Yeah, I'm equidistant, right? I'm 10 volts away. 5 volts is 10 volts away from 15. 5 volts is 10 volts away from negative 5. So I'm right down the middle. So I like to double check that. So I have an offset of 5 volts. And if you do the average universal formula here, you can plug this in, half the time I'm at 15, half the time I'm at 5. Overall, my average voltage would be 5 volts. And you might notice something, and you'd be right to say the offset and the average are the same. For these two examples, that's true. And for any rectangular waves, well, square waves, I was going to say for any rectangular waves that are symmetrical in time, that's a square wave. But waves in general that are symmetrical in time, in other words, the amount of time you spend at each peak is the same. As long as that's happening, then this will always be true. Offset and average will be the same number. That's true for sine waves. It's true for any waveform that's symmetrical in time, meaning equal time at both peaks. So square waves and sine waves are symmetrical in time. So we'll get to that in our other video. We'll talk about sine waves directly. But for this example, yes, I have this little note here. Offset and average are identical. Same number. Yeah. And again, RMS is very different than average. So your average voltage, we can see it maybe even without the formula, but if we use the formula, we get 5 volts. Now when you use this universal formula for RMS though, you can see it's very different, 11.18 volts. Remember, you square the voltages, so you'd have 15 squared, and half the time you're there, and you add that to 1/2 of 5 squared, right? Because half the time you're there. These are just the the 4/8 and the 4/8. So, and then you square root it. And sometimes it's surprising. But maybe the result, I don't know. It's not always intuitive to me when I see where RMS puts me. But if you question it, you can always take out a little resistive load of any type, or a big resistive load. Works big or small, but you can take a small lamp and take a 12-volt lamp and hook it on to this waveform. And then also for comparison, you could hook it on to 11.18 volts DC. And if you put the two lamps, the 12-volt lamps side by side, they should look identical. They should be burning the exact same brightness. All right, let's head to this example. What do we have now? Maybe 3 times longer. It's at 10 volts and then negative 10 volts. And again, remember, for resistive loads, it doesn't care which direction current's going. So overall, it's going to see 10 volts for 3 milliseconds, maybe, if we use milliseconds. And then it's going to see negative 10 volts for 1 millisecond. But remember, without caring about polarity, it's just 10 volts all day long, right? 10 volts and 10 volts. So your offset here in this one is 0. It's centered on 0. My average voltage, interesting, right? It's not 0 because 3/4 of the time it's at 10, and 1/4 of the time it's at negative 10. So I really have 7.5, 3/4 times 10, right? You know, that's this over here. 3 out of 4, 3/4 of the time I'm at 10 volts. 1/4, 1 out of 4. The period's 4. So 1/4 of the time I'm at negative 10. That's negative 2.5. Add them together, 7.5 and negative 2.5, right? Did I go too fast there? I could have written that down for you, huh? So we're really saying 3/4 of the time, 3 milliseconds out of 4 milliseconds, I'm at 10 volts. And 1 millisecond out of 4 milliseconds, I'm at negative 10 volts. Then do the math, 3/4 of 10. So I've got 7.5, right? 7.5 plus 1/4 of negative 10 is negative 2.5 volts. There we go. Add them together and you get 5 volts right here. And that's not what a lamp would look like if you hooked it on there. It's not going to look like it's burning with 5 volts of voltage. So average, again, does not really describe the DC equivalent circuit at all. But RMS tells the truth, 10 volts. It's going to be 10 volts all day long. And RMS, you could get it here if you wanted to do it here. It would just be, 3/4 times 10 squared would be 100. And plus 1/4 of 10 squared, another 100. You see, the squaring is what takes care of it for us here to give us that real world, what it's going to look like in the real world with electrical characteristics. So squaring does that for us. It takes into account the fact that what we've been saying, that the lamp doesn't care which way the voltage's polarity is. So that's what the squaring here does for us too. So it does a lot of things for us. It gets us the similar power calculation because it's V squared over R, but it also gets rid of that negative real handily. The fact that you don't care that it's going the opposite direction. So this becomes 100, this becomes 100. 3/4 of 100 plus 1/4 of 100, right? Sounds like 100. 100 square rooted is 10, right? Try them out. If you're following those examples, again, I could have written that out for you, but I think you're getting it. And I kept the numbers simple on purpose. I hope I'm not going too painfully slow in this video. It might be too simple, but that's the idea. I wanted to keep real simple examples with simple numbers. But run the numbers for yourself in these problems, and just remember these universal formulas and use these for activities and stuff. Just come right to this. Maybe jot these down in your notes. Our book actually does not address RMS for rectangular waves. It runs a little bit of practice problems for you with average, but it doesn't address this. So this is kind of important to get into your notes. It's not that much more to add, is it? But it's nice to have. Okay. Okay, let's take another look. We're almost wrapping it up here. Here's an example, right? 3 milliseconds again, maybe in just 1 millisecond. But now I'm at 15 volts and negative 5. There is offset. Center is at 5 volts, right? That's the middle of the waveform. So I've got that. My average voltage, if you plug it in here, what, 3/4 of the time I'm at 15, and 1/4 of the time I'm at -5. The average actually turns out to 10 volts. You can try it. You can plug them in here. I kind of already have numbers stuck in there, so I'll leave that alone. But try it. Do you come up with 10 volts average using this formula? You should. And then RMS, again, you would say to yourself, I can come over here and do that one for you. What do we have? Maybe 3 milliseconds out of 4 milliseconds, you are at 15 volts. So you'd have to square that 15 and take 3/4 of it. 1 millisecond out of 4 milliseconds, you are at -5 volts. So square that, right? And notice the negative goes away when you square it. So -5 squared is 25, right? So 1/4 of 25 and 3/4 of whatever 15 squared is. So run those numbers. You should come up with this 13.23 volts for your RMS. Notice in these two cases, offset and average are now not the same thing because we've lost our time symmetry, right? These are not symmetrical in time. So offset will not be the same thing as average. I've got an offset of 5 volts, but I got an average of 10 volts. Yeah. Okay. Last one. Kind of an interesting example, I guess. You have, now we're only spending 1 millisecond at 15. We kind of flipped it. From this example, we changed to the pulse width is now the short amount of time. So 1/4 of the time you're here, 3/4 of the time you're down here. The offset is still 5 volts, but look, the average is 0, right? Because some of the time I'm at 15 volts, and that's high, that's a higher voltage. And some of the time I'm at -5. Can you see that I'm at -5 3 times as long as I'm at 15, right? That's why overall the average is 0, right? Sure, I'm at 15 volts, but for a short time, and then 3 times, I'm only at -5. I know it's only -5, but I'm there 3 times longer, so that cancels with the 15. So average is 0 overall. And again, if you see those things sort of just by looking at it, or if you don't, no problem. You know, that's what you got this formula for. You know, plug the stuff in. Remember, the offset's the middle of the waveform. So there you have it. They're not the same, offset and average and RMS are not the same, of course. But it's interesting to see that the average formula tells you, oh, you got an average of 0 volts there, but if you put a lamp on there, it's going to burn with a brightness of 8.66 volts as if you applied 8.66 volts DC to it. Yeah. So that's the main thing about this video, just to really emphasize these 3 parameters, which sometimes offset and average are the same thing, and then sometimes they're not, and also to emphasize that average and RMS are very different animals. Yeah. All right. What you can do with this is create some of your own waveforms using maybe whatever you could use graph paper to sketch a couple, or just freehand it. But sketch some if you want to, and try some calculations. And then more importantly, get the Analog Discovery to generate some waveforms of your own. So just create your own rectangular waveform. It could be a square wave. That's sort of a subset of rectangular wave. It's a rectangular wave that's symmetrical in time. It's a square wave. But put some of this to use. Create your own rectangular wave an actual wave with the Analog Discovery wave generator, and then bring that into your oscilloscope, connect the wave generator output to your scope, and use the measure menu of your Analog Discovery to perform the measurements on that waveform. You can look for the center, that's easy enough, but then the Analog Discovery can also measure the average voltage and the RMS voltage. And you can match it up to the theory that you can do here now that you know these formulas, and it'll give you practice creating the waveform in the WaveGen of the 82. It'll also give you practice dialing it in and getting it to display on the scope, and it'll also give you practice pulling that measure menu out and doing actual measurements on waveforms, because we're going to be doing a lot of that in the AC course. So it helps you get all those sort of skills going. I think I remember in the Analog Discovery, in their measure menu, I think they had something like AC, RMS, and DC RMS, and that's a little confusing. I think I'll have to research that a little bit. This is the one that's going to be the true RMS. You can think of it as direct coupled RMS. Is what the DC would be, which means the DC RMS is going to include everything that's in that waveform. The AC RMS measurement is probably just the measurement, it's probably just the RMS of the AC portion of the wave, which means the offset is ignored, and that's not what we want. We want to know the true actual DC equivalent RMS. What's the equivalent voltage that you would use for DC or this waveform? So this is the one you want to look at when you're looking at the measure menu. AC RMS, like I said, is probably just the RMS of the AC part of the waveform, and it ignores what would be called the DC part of the waveform. Is also also known as the offset too. We'll get into that, but they'll sometimes call it the DC offset. It's if you add DC to an AC waveform, that's how you put offset into a waveform. Okay. Well, I think that's enough for this video, and then I'll do another video on sine waves that helps you sort of dial in on those parameters, and we'll do the same thing. You can generate your sine waves in the 82 and do some measurements on those as well, but this will be a good start.